chat first, and then if Jingjiang, you can also start one. Done? Okay, great. So welcome back everyone to the symmetry seminars. We had a summer break, and now the new term will start off with Theo Johnson-Freyd from Dalhousie perimeter, and he'll tell us about a 4D TQFT that is not quite a gauge theory. So please take it away, Theo. Thanks.
Thank you, Sakura and Lakshya, for the invitation and for the opportunity to speak. If you want to go through these slides at your own pace, they're online, and there's also a link from my website. Yeah, so I have 14 actual contentful slides. I'm going to tell you exactly what this says in the title. I'm going to tell you about a 4D TQFT, which is almost but not quite a gauge theory. Here's the complete list of content slides. I'll sort of say some words that are actually about the main point of the talk, and then the rest of the talk is just like technical details that you can ignore if you decide to. So let me dive in. So the goal that I want to tell you, as I said in the title, is, well, the overall goal of the talk and the project that I want to tell you about is to kind of do a detailed study of exactly which four-dimensional TQFTs are really gauge theories. And you might think this is a funny question for me, of all people, to be presenting on, because I might have a paper that did something towards proving that every 4D TQFT is sort of a gauge theory. And so what I really want to do is tell you some subtleties in this classification of 4D TQFTs, although I may have been involved in it. The classifications really due to Lan, Kong, and Wen. And then, so there's two papers. There's a paper of Lan, Kong, and Wen, and then there's a paper just of Lan and Wen that followed up on it. And really all the main ideas are already in those papers. My contribution was to fill in some mathematical steps, sort of to kind of move the statement to a more mathematically precise foundation. And the punchline of the talk that I'm going to tell you is the following. So the issue that I'm going to try to emphasize is exactly what we mean when we talk about gauge theories in 4D TQFTs. And I'd like to flag a reasonable but wrong statement. And it's a statement that has been made in the literature, so that's why I think it's worth really flagging. So some people will consider the theory I'm going to present to be a gauge theory, but it's not what I'm going to call. I want to sort of be more precise and say, let's agree that a true gauge theory is something, maybe a topological, maybe finite. Maybe I should have really put the word finite in here. I'm only going to talk about finite, kind of very finite objects, very topological objects. But let's say that a true gauge theory is one where I really give you a gauge group, maybe a higher form group, that's fine. And I really give you some Digraph-Witten Lagrangian, and then you are supposed to go sum over G bundles with a term in the action use the Lagrangian, use the Digraph-Witten action the way you're used to. And these are the things I want to consider a true gauge theory. More generally, I want to consider a true gauge theory anything that really is given by, I give you a group and I ask you to sum over G bundles, as for the path integral. So I think I have a footnote that you can't see because of how Keynote says that in higher dimensions, where you'd actually be able to put it, well, you can download the slides. It doesn't matter. There's some footnotes here I'm not going to talk about. But that's what I want to say is a true gauge theory. It's something where you really are summing over G bundles, as opposed to something that might have some G bundles and maybe some spin structures or something else. Those I want to think of as maybe kind of false gauge theories. And I want to make this distinction in the talk. So now that I've explained what I want to consider a true gauge theory, let me tell you what the Lan-Kong-Wen classification of 4D TQFTs actually says. So the Lan-Kong-Wen classification of 4D bosonic TQFTs, this is well, this was in a footnote before, but I then forgot to copy it. This is for bosonic TQFTs over C, over sort of any algebraically closed field of characteristics 0. And there's a few other footnotes on the previous slide. Every bosonic TQFT with some niceness conditions is exactly one of the following two things. Every bosonic TQFT is either of class that Lancong and Wen call class AB. AB is their name for the all bosons case. And those are really true gauge theories. And not only are they true gauge theories, they're true gauge theories for just a zero form group. There's no higher groups or anything. These are the ones that Digraph and Witten already knew everything there is to know about. And then the other class of TQFTs that they found are ones that they call emergent fermion TQFTs, EF TQFTs, and they're more complicated. The distinction here, as I said, the distinction, which is, as I said, this is really Lancong and Wen work. The all bosons case means that so one of the basic data in a TQFT is the line operators in the TQFT. The spectrum of line operators does not tell you the whole spectrum of the whole TQFT. There's missing data, but it tells you a lot about the TQFT. And the AB case is when all of the line operators are bosons. And the EF case is when some line operators behave like fermions. And I want to distinguish this. This is not to say that it's a fermionic TQFT. It's not a super TQFT. It's a bosonic TQFT. It's something that lives with, like, the Hilbert spaces are just bosonic vector spaces. It lives on oriented manifolds. You can still have fermionic lines in an oriented in a bosonic TQFT. You can have line operators which braid with themselves for a sign. So anyway, and most of my talk will be to sort of go into some detail about the structure of these things I'm going to call spin gauge theories, this other class. I haven't said much about it, but roughly speaking, well, literally speaking, it's the following. A spin gauge theory is the following. You take a group of, there's sort of a gauge group, if you want to call it that, which is not just, which it comes as a central extension of, with a Z2 central subgroup, and then some quotient group. And then if you have any group like this, any group Z2.G, then you can write down, if for the people who like tangential structures, what you do is you write down spin kind of times over the Z2 that lives inside of spin with GF. So spin, you should also think that spin is another group of this shape. It's a group of shape Z2 by SL. And so a spin GF structure, a spin GF bundle is a reduction of structure to that group. And a spin gauge theory doesn't sum over G bundles, it sums over reductions of your structure group to this spin GF group. And kind of if you're, this is like not a quite correct thing to say for finite groups, but like the way you should think about a spin, like the data of a spin GF bundle, is that a spin GF bundle is like a regular old GF gauge bundle, except that the connection isn't flat. Instead, it has curvature. Now, this is like totally doesn't parse, because these are finite groups, and finite group bundles don't have like non-trivial connections, but that's the way to think about it. And you can write these down by kind of taking a Lie group with a connection where you force the connection to have prescribed curvature and then Higgsing something. Anyway, so this is almost a gauge theory. Like they have the word gauge theory in the title. And this slogan that I was involved with popularizing, that all 40 TQFTs are gauge theories, that slogan a priori requires that you treat these spin theories as gauge theories. If you decide that that's a type of gauge theory, then you can, walk away from my talk. And you're like, okay, they're all gauge theories, I'm done. But if you think that gauge theory should really mean an integral over gauge fields on the nose, then a spin gauge theory at least isn't a priori a gauge theory. It's something else. Okay, so fine. So this is their class. This is what the theorem actually says. And most of my talk will be to go into quite a lot of detail about how to classify spin gauge theories, what the homological classification of them is. But I want to sort of raise a possibility. So at least some spin gauge theories are actually equivalent. They're like dual to, or you know, the word dual means too many things and we should have never used it, but by now we use it for half of like, anyway, one of the many things dual means, as I think everybody in this audience knows, is when you have two isomorphic field theories that are just exactly equivalent as quantum theories, and they just come with different descriptions. So a spin gauge theory is a particular description of a gauge theory when I've presented it to you as a spin gauge theory. And some spin gauge theories absolutely are equivalent to, they are isomorphic to honest true gauge theories. The true gauge group, like if you're writing down an equivalent true gauge group, you're forced to use a higher form group, but that's okay. It's the 21st century. We all know about one form groups and higher groups and so on. And the first example of this is that just plain old spin Z2F gauge theory. So spin Z2F gauge theory, when you don't have any other group, this is the theory of a dynamical spin structure. Like the path integral literally just takes an oriented manifold and sums over all possible spin structures you can put on that manifold. And that's what it does. A spin structure is a lot like a Z2 bundle. You know, the difference between two spin structures is a Z2 bundle. So spin Z2F gauge theory is a lot like just ordinary Z2 gauge theory. And so this is a perfectly kind of ordinary quantum theory. It turns out that spin Z2F gauge theory is isomorphic to a true gauge theory for a one form group, just Z2 in degree 1. So this will be my notation for Z2 thought of as a one form group. And now you can go and ask, well, what are I'm special in degree 4. In general, this one is 4 minus 3. And this 4 is the space-time dimension. And you can figure out what degree would be if you, so what am I saying? If you had just like say regular old Z2 gauge theory in dimension 4, say with trivial Digraph-Witten action, regular old Z2 gauge theory in dimension 4 is dual, it's kind of electromagnetic dual to Z2 one form gauge theory in dimension 4, also with the trivial Lagrangian, with the trivial Digraph-Witten action. And that, if you remember the numerics for how to do electromagnetic duality for ordinary ungauge theories with no Digraph-Witten Lagrangians, that'll also tell you the numerics for doing it for the spin theories. So that's why you can figure out that this is a 1. And then the only thing that's interesting is that somehow the fact that this is spin Z2 gauge theory and not plain Z2 gauge theory, not true Z2 gauge theory, what that shows up with in the dual description is it shows up with a different Lagrangian. And the total possible, all the Digraph-Witten actions for Z2 one form theory in dimension 4 are indexed, well, the Digraph-Witten action has to live in the fourth group cohomology. The fourth group cohomology of this one form group, this is, you know, a mathematician wouldn't like the way I've written it. A mathematician would have preferred me write this as H4 of K Z2 2 with U1 coefficients. This group is well known. This group was calculated back by, I don't know, Eilenberg and MacLean in the 1950s. Actually, probably a lot long before that. This particular group was probably calculated as soon as cohomology was invented. I don't know, something like Noether, you know. I don't know. Well, anyway, this particular group must go long before the 1950s. But Eilenberg and MacLean already give you all the technology you'd need to calculate this group, and it's a Z4. And the number, this is, there's a distinguished class, other than the trivial class, there's a distinguished class that is a stable class called -1 of the SQ2. And this class this is a class that lives as long as I said, this 4 is this 4, and this 1 is 4 minus 3. And if you change, and then this class lives for any value of 4, the other classes don't live in higher dimensions. And this is always what it is. It's always this, whether this is a Z4 or not depends on what dimension you're in, but there's always this class. This is, by the way, this is the class that's like 2 out of Z4, 2 mod 4. So anyway, this is something you can do for just plain Z2 gauge theory. And then there's this suggestion in the literature that is very reasonable, actually. It's like a very reasonable idea that says, well, let's take our spin GF gauge theory. All the spinny stuff has to do with Z2F. The rest of the group is really just behaving basically like some sort of ordinary gauge group. And let's, maybe you open up Tachikawa's paper on gauging finite subgroups. Maybe you open up Tachikawa and Laksha's paper that preceded it, and they tell you how to pick up subgroups of gauge groups and just replace subgroups by their electromagnetic duals and get another dual gauge theory description for the whole thing. I mean, they didn't say it in terms of the sort of bulk gauge theory. They said it in terms of boundary theories and their anomalies, but those are the same. So you open up the paper and it looks really reasonable. It says you pick up this, okay, they didn't talk about spin gauge theory, they talked about ordinary gauge theories, but it seems like it should all just work out. You just pick up this thing that's almost a gauge theory, you write down a true gauge theory dual for some subgroup, and you should get a true gauge theory dual for the whole gauge theory.
Theo.
Great idea. Yeah.
I have a quick question.
Yeah.
Is the extension the same between like Z2F and then the Z2 bracket 1 if you take the dual? Is it still using the same extension information?
Great question. So it can't be quite the same because an extension of this type was classified by, like, this extension data lives in H2 of G with coefficients in Z2.
Right, so the latter is like an H3, right?
This extension data lives in H3 of G with Z2. So there must be some rearrangement of data if you could do this. And you sometimes can do this. I don't want to tell you that you can never do this, but at least some of the time you can certainly do this suggestion. And the way, when it works, maybe always, I haven't convinced you that it doesn't always work. Maybe you believe something like this will always work because lots of similar situations, something like this does always work. And in general, there's some rearrangement of data that where, like, the extension data here becomes part of the Digraph-Witten action here, and the extension data here is extracted from the Digraph-Witten action there. And there is some sort of systematic way that that would work. And the punchline of my talk, the sort of thing I want to tell you, is that this does not always work. That sometimes you can take a GF gauge theory, a spin GF gauge theory, and write down a true gauge theory for some dual group, and sometimes you cannot. And I'm going to tell you an obstruction to this. But when it works the way, basically the way that Bhardwaj and Tachikawa say it should work. I mean, up to like putting in some extra -1 to the SQ2s or something. And maybe, okay, maybe I'll, maybe you think that, oh, maybe there won't be something that maybe this doesn't always work, but then you could ask another question. Maybe just extensions of this form is too naive. Maybe you won't catch all 40 TQFTs with just gauge groups that are mildly higher form. Maybe you'd be able to catch all 40 TQFTs if you allow more complicated higher form groups. And I'm going to tell you that no, you don't get, you can't. That they just, like, there are, the 40 TQFT I'm going to tell you cannot be written down as a true gauge theory for any higher form group, even though it's going to be a completely mild as a spin gauge theory. Okay, so that's the thesis statement of my talk. So let me start giving you some more details. So I'm going to tell you a specific spin gauge theory. It's for a specific very mild group. There will be just a Z2F that's like not even extended. It's just going to hang out. So this will just give you a sum over spin structures. And then the rest of the gauge group is a totally mild group, just Z4 squared. It's this nice abelian group of order 16. And I'm going to give you a gauge theory, a spin gauge theory for this group, which I can prove is not equivalent to any true gauge theory. So let me tell you a little bit about how I'll build this spin gauge theory, just so you really have it in your hand, so that you could go away and like ignore me for the rest of the talk and go try to build it yourself. And to do that, I have to remind you a bit about how spin gauge theories are classified. And there's a comment in the chat.
Yeah, there's a question. Apparently my microphone isn't working properly, but I had a question on the previous slide. Is Z2F always normal in GF? Great,
yes. So whenever I write extensions like this, this is a sort of notation that I picked up from the finite group theory literature. So this means an extension with a dot in the finite group literature means any extension where the left person is normal and the right person is the quotient. And because it's Z2 and not bigger, normal is the same as central. If it were bigger, then this would just mean a normal extension. And the sort of Tachikawa and Barboj-Tachikawa technology works particularly well when you have a normal subgroup. If you try to kind of play their games for subgroups that aren't normal, your choice of subgroup breaks some symmetries in your theory, and so it's less good of a game to play. You're kind of for these normal subgroups, it works very well. And I'm going to use that same notation for okay, crazy. There's like this weird, somehow Keynote has decided to leave a red dot. Okay, whatever. I'll use that same notation for higher form groups, although a finite group theorist maybe doesn't like higher form groups, but physicists do. So. And we get to, well, you all get some good notation left and right. What is going on with my Keynote?
Yeah, it's stuck there now.
Okay, we're just gonna tolerate that there's just gonna be a dot there. Okay, so I want to tell you a little bit about how to classify spin gauge theories, and then a lot of the talk will be kind of going into some detail about this type of classification. And I think a nice place to read about this is there's a paper by Gaiotto and Kapustin that studies this problem. They didn't quite say that this is what they were doing, but this is what they were doing. And really what I'm telling you about is a cohomology theory that it's a funny thing. It was a cohomology theory introduced by Wang and Gu based on work of Gu and Wen. And those papers, Gu and Wen and Wang and Gu, called it supercohomology. The cohomology theory in question is much, much older. I mean, it probably goes back to Tom or so the mathematicians have known about it for 100 years, but it didn't have a single name as far as I can tell before these physics papers. So, right, so the classification is the following. So let's suppose that your group GF is an extension classified by some cocycle kappa. Then there is a cohomology theory called supercohomology twisted by kappa. And it makes sense in any dimension. I'll tell it to you in dimension, I guess I'd tell it to you in dimension bullet. So a cocycle, when you tell a cohomology theory, there's this sort of neat stuff from the mid 20th century to point out that actually to tell you a cohomology theory, all I have to do is tell you what the cocycles. I never actually have to tell you what the co-boundaries are. There's like a unique way to take what the co-boundaries are. So I'll just tell you what the co-cycles are, and then you have to go away and work at the whole cohomology theory. So a co-cycle for twisted supercohomology consists of the following 3 layers of data. And I call them layers because they kind of live in different homological degrees. So at the top, there is a Digraph-Witten layer, and which is just an ordinary cohomology class in the base group with coefficients in U1. And if you didn't have any of the rest of the layers, then this would just solve dA is 0, or dA is, I guess, 1, because I'm in U1. But I modify the equation. I actually don't demand that the Digraph-Witten Lagrangian be a cocycle. Rather, I demand that its differential be something explicit in terms of the lower layers. And then the next layer below the Digraph-Witten layer is what Gu and Wen had studied in their paper that I think was actually the first paper to use the word supercohomology. And they said, well, we could additionally have a cochain of degree 1 less than the dimension that I care about, just valued in Z2. And they didn't know about the bottom layer, so they would have written down dB equals 0. And then the Digraph-Witten layer's cocycle formula gets modified there. And then Wang and Gu pointed out that it was very natural to add a 3rd layer that I don't think they gave a name for it. I mean, these words, the Majorana layer, the Gu layer, and the Digraph-Witten layer are the names that, I think they were the names that Anton and Davide were using. Certainly by the time David and I wrote our paper on generalized cohomology theory, they were already in Davide's head. I'm not sure the history of these names. We call it a Majorana layer because it really does have something to do with coupling to a Majorana spin chain. And so the full data is those 3 things. There's a cocycle. Well, it's a cochain, but it solves the equation that d of it is 0. There's a cochain which fails to be a cocycle in some explicit way. And there's another cochain which fails to be a cocycle in some explicit way, except it's not very explicit because I've never actually seen anyone write down the complete formula. Maybe people have, and I haven't found it, but whatever the kind of last term is, it's some garbage involving like primitives of Adem relations. So you actually really have to dig in. Like I've tried to come up with a good formula so that I could put it on a slide, and it's garbage. It's like you have to like write down, like it has the following flavor. You take like SQ2 of SQ1. These are Steenrod squares of gamma. That's some class in degree in Z2 cohomology. Then you just like take this. This is a perfectly good cocycle, but this lives in kind of cocycles with coefficients in Z2, and then you kind of arbitrarily lift this to a cochain with coefficients in Z4 just by kind of deciding that 0 is going to go to 0 and that 1 is going to go to 1, and you ignore the fact that that's not a homomorphism, and then you take like, square root of -1 raised to that power. And it's some garbage like that, and maybe that's not quite it, but it has that type of flavor for this term. Anyway, it doesn't really matter what this term is because we have better ways of analyzing what one of these cohomology classes looks like. And now I'll just tell you the way you build the cohomology theory, the spin gauge theory that I want to tell you about. My claim is that if you pick any cohomology class like this, which has the property that, so one of the things you could do from a supercohomology class, just from the way I've presented it, is that given one of these kind of triples of cochains, you could just ignore the top 2 layers of the cohomology class. And you could just remember just the bottom layer, just gamma, just that cocycle. That is a cocycle. So it really does write down cohomology class. And now what I want you to do is go in, solve some this is some kind of cocycle equations, go in and solve them and find a supercohomology class whose bottom layer is non-trivial. And I claim that once you've done that, you will, that supercohomology class will give you an example of a spin gauge theory, which is not an actual gauge theory. That's my claim. So it's in principle completely explicit. To the extent that you know how to solve these equations, it's completely explicit. Okay, so as I just repeat the claim here. So to convince you that this works, I need to convince you two things. I have to convince you that there really is such a cohomology, such a supercohomology class. Like, maybe there just aren't solutions to these equations. Maybe the right-hand sides just are not trivial in cohomology, and so you wouldn't be able to solve them. So I have to convince you that there is such a cohomology class, and I have to explain why this obstructs having a true gauge theory description. And the rest of the talk, I guess I've used half my time. I think I'm supposed to go for an hour. Is that right?
Exactly,
okay.
Yes. But you can take your time. We're not that strict.
So for the second half of my talk, I'm going to give some of these details. If you're happy just believing me that if you're happy kind of trusting that I'm an honest person, then you can kind of go and do your crossword. But if you want to see how this type of argument works, then I'm now going to kind of dive into some of the details. But maybe this is a good place to just sort of pause and see if there are any questions, because we're halfway through the talk.
Sorry, I have a simple question.
Yeah.
Is your notion of gauge theory equivalent to say that the TQFT has gap boundaries?
All of my TQFTs are, my definition of true gauge theory was that a true gauge theory was something, I'm only doing finite groups, and so my definition was that a true gauge theory was something that admits a description, admits a Lagrangian description in terms of a finite, possibly higher form group, and then the path integral literally integrates over G bundles and not some more complicated twisted G bundles. That was my definition. Now, if you have any Lagrangian theory like this, then true gauge theories always admit a favorite boundary condition called Dirichlet boundary. And for finite group theories, that Dirichlet boundary is definitely a topological boundary condition. But that's somehow a consequence of the fact that it's a true gauge theory.
So you're saying that there might be theories which still have gap boundaries, but are not true gauge theories in your language, right?
That's correct. So in fact, the theory I'm going to tell you, in fact, also all the spin gauge theories admit topological boundary. They don't admit a pure Dirichlet boundary, but they admit a boundary which is like Neumann for the Z2F fields and Dirichlet for everything else. Yeah, I told you a classification of 4D TQFTs, and I was actually only telling you a classification of 4D TQFTs which admit a gapped boundary. I said there were some footnotes that I left out on the first slide. And that was one of them. I think I do know the classification of, there's also 4D TQFTs which don't admit gapped boundary. And they can't because they have a -1 to the W2, W3 anomaly. And I think I know how to classify those as well, although there's like one spot in one spectral sequence where I get confused. I know in principle how to classify those as well. And but I'm not considering those in my talk. So all of the gauge theories I'm telling you are all the TQFTs I'm telling you have trivializable gravitational anomaly. They admit gapped boundary. They are as good as you could ever want.
So, sorry, I'm a bit confused because maybe this is not true, but it isn't true in 4 dimensions that having a gap boundary is equivalent to say that there is a subgroup of the possibly higher group global symmetry, which can be gauged to trivialize the theory.
Right. So
in 3 dimensions, at least this is true.
Yes. yes. I mean, this is true. So as I said, like a spin gauge theory doesn't have a pure Dirichlet boundary. The pure Dirichlet boundary would be somehow either the whole subgroup or something like that.
Oh,
It's
okay.
getting,
Okay.
is getting broken at the boundary. Whereas the spin gauge theories have a kind of mixed Neumann Dirichlet. It's Dirichlet for the kind of the sort of it's like Neumann for the Z2F fields and then Dirichlet for the rest.
Okay. Thank you.
Hi, I have a question. So
Yeah.
what about the higher group cases, like 2-group or 3-group gauge theory?
Right. So what I'm going to tell you in the kind of third half of my talk is that no matter what higher group you want, you won't be able to pick up this one.
Oh, okay. So that
It's
also fits into
beyond
this
higher
part.
group gauge theory. Yeah.
Oh, okay. I see.
Okay. So let me go in and kind of lightning, or well, not too lightning, in 20 minutes tell you the second and third halves of my talk, sort of how to do this. So first, let me tell you why there is such a class, because I think that's actually that might be the more interesting part for a kind of practitioner audience, someone who actually wants to compute things. So let me just tell you in general how to solve this type of problem. So the problem I want to know is I pick up some finite group. In the case I care about, it's Z4 squared. And I have some interesting map of cohomology theories. It's the map that takes me from, oh, this B was from an older version of the slide. G is equal to GP. So I pick up some finite group and I want to know, or just some space or whatever, and I want to know what is the image of this map of cohomology theories that takes me from a supercohomology class just to its bottom layer. And the way you do this type of thing is the following. You recognize that this is a map of cohomology theories. It's not just a map from degree 4 cohomology to degree 2 cohomology. This is part of a map from degree bullet cohomology to degree bullet -2 cohomology. And anytime you have a map like that, then you can answer this type of question by abstraction theory. And the specific version that I'm doing, it's a comparatively easy thing. So remember that my supercohomology theory, what I called had 3 layers. And I'm basically just trying to ask, what is the image under mapping to the bottom layer? Well, what you do is you ask, instead of trying to answer what's the image, you instead try to answer what's the kernel. And cohomology theories are this beautiful thing that let you basically, right, if you think back to when you took like undergraduate linear algebra. I'm sure that even physicists took undergraduate linear algebra. And when you took undergraduate linear algebra and you asked for you had matrices between finite dimensional vector spaces. And you knew that you could, if you knew the dimension of the domain and the dimension of the range, you could the dimension of the domain and the dimension of the codomain, you could figure out things like what's the dimension of the image and what's the dimension of the co-kernel if you know the dimension of the kernel. There was some dimension formula like that. And anything that was basically true for linear algebra is also true for cohomology theories. And cohomology theories are designed to have this type of technology. So that's what I'm going to do, is that instead of asking what is the image, I'm going to ask what's the kernel of the map. And the kernel of this map, well, the kernel, this is the map that just writes down the bottom layer. So the kernel sure looks like it should be something that has only the top 2 layers. Now there's some subtleties because I'm passing freely between cocycles and cohomology classes. But again, the theory of cohomology is designed to smooth all of that out. So what I'll do is I'll write down an older version of supercohomology. This is the one that Gu and Wen originally wrote down. I'm going to call it restricted supercohomology, which is the cohomology theory that just has 2 layers. The bottom layer is just an ordinary cocycle, and the top layer solves d alpha is -1 of the SQ2 beta. And if I had a kappa in there, I would have added kappa cut beta, but for me, kappa equals 0. What just happened? And I lost all of my squiggles, but I also lost that annoying note, or that annoying red dot. Okay, so yeah. So I would have, as I said, this would have had a plus kappa cup beta, but kappa equals 0 for the group I care about because of this times. That's kappa equals 0 case. Otherwise, they're with an extension. So this is the thing I'm going to call restricted supercohomology. And what cohomology theory, sort of the theory of cohomology theories tells you is that there's a long exact sequence. So what you get from this description is a short exact sequence of cos on the level of cos cycles, and short exact sequences of cos cycle theories give you long exact sequences in cohomology. And the long exact sequence compares, well, it has the group we actually care about, the actual supercohomology. It has the thing that writes down the Majorana layer. It has the restricted supercohomology, the kernel mapping into the full supercohomology. So that, like, this part going to here would have been a sort of short exact sequence of coefficients. This is what you would have seen. And then cohomology theory says that there's a connecting map that I'm going to call the obstruction. Because what this map literally does is it picks up a class in just the bottom layer. It does some complicated calculation, and it writes down a class in restricted supercohomology. And the fact that this sequence is exact tells you that this complicated calculation exactly measures whether the class I care about is or is not in the image of supercohomology. So let me just sort of summarize this slide. What I've told you is that to answer a question like this, to answer what is the image of a map like this, and to measure that image is to understand this obstruction map and to know how to compute it. Okay. So now let me just sort of emphasize again that, like, this is a thing that picks up, say, in the case I care about, a degree 2 class in ordinary cohomology, and writes down something with only 2 layers. There's just 2 obstructions, a Gouin layer and a digraph-Witten layer. So it's a comparatively easy calculation to do. And importantly, you never really had to know what that formula involving gamma on the slides a couple times ago was, or at least you can hope to not need to know. You can hope to sort of avoid knowing it, which is the whole reason I'm doing this. Nitu asks, is it a coincidence that alpha and beta something might correspond to bosonic theories? I think that's a coincidence, Nitu. I think that what happened was, yeah. Well, I'll say in a moment where alpha and beta are coming in. Maybe you'll decide that my answer is yes, but so far this is still about supercohomology. It's still an ordinary cohomology theory, like a purely bosonic thing, should be just having top layer. Okay, so now I'll just start quoting facts. So what I want to do is to show the following. I wanted to show that Majorana had a non-trivial, that this map was non-trivial. I wanted to show that there was a non-trivial image of this map. So to show that this map is non-trivial is the same as to show that the obstruction map has a non-trivial kernel. So that's what I want to do. I want to prove that the kernel of this obstruction map is not 0. That's all I need to do. And I'm going to give you an explicit class in this. So let me do it. Okay, let me remind that for this group from Z4 squared, I know its cohomology very well. It's some polynomial ring in a couple generators with some relations. So the capital letters are in degree 2, the lowercase letters are in degree 1, and x squared and y squared are both 0. And there's an interesting degree 2 class, which is the product of the 2 degree 1 generators. This is the unique sort of essential class in this cohomology theory, or for this group. And I'm going to claim that this class has 0 image under my obstruction. So now let me try to measure that. Well, again, restricted supercohomology itself has 2 layers. And so I can write down a top layer and a bottom layer. I mean, I can write down the bottom layer, in this case, the Gouin layer. And here's Wen chiming in with some more details.
So Shao, you can just unmute yourself.
Yeah. Well, I'll keep going, but Xiaogang we'll have some conversation afterwards. So restricted supercohomology that Xiaogang invented has two. A restricted supercohomology class has two layers. It has the beta and the alpha layers that I called them, and so in particular, there's a map that takes the whole supercohomology class to just its beta layer. This is alpha beta maps to beta. Remember that beta is a cocycle in ordinary cohomology, so that's a valid thing to do. Alpha is not a cocycle in ordinary cohomology, but it solves d alpha as something about beta. So alpha comma 0 is a valid cohomology class. So that's what these two differentials are in terms of cocycle. What these two maps are in terms of cocycles. So there's a long exact sequence like this. And the connecting map is square 2. Actually, it's not square 2. That's wrong. It's -1 to the square 2. This operation -1 to the square 2 shows up like everywhere in the world of spin theories. And I happen to know, actually, because I told you when I told you the sort of part of the information of full supercohomology, I secretly told you the composition of taking the obstruction to the full restricted supercohomology and then going down to the beta layer. And what it was SQ2. This was the SQ2 connecting the gamma to beta. So this is where gamma lives, and this is where kind of beta lives. And if you remember, the formula was that d beta was SQ2 gamma, and this is what you're seeing. Well, in the particular case I care about, SQ2 of x squared is, well, SQ2 of a square, well, square 2 in degree 2 is just the squaring. So square 2 of x squared is x squared, sorry, the square 2 of xy is xy times xy, but x squared and y squared are both 0, so that's 0 times 0, which is 0. So this layer vanishes. And so that means that the obstruction class I care about, its image is 0 under here, so it must live in it must be a purely kind of digraph-Witten, a purely U1 ordinary cohomology class. And then the last step is actually that specifically, it doesn't live here, but it lives in the quotient of this by the image of the previous differential, and then you just compute that, well, so it lives, I guess the actual group I care about lives, the class I care about lives in this quotient. It lives in ordinary cohomology modulo the image of square 2. And again, this square 2 is, this is wrong, this is square 2. So the slides are wrong. And then there's one last trick, which is that if you think back, I said, well, it was 0 times 0, which is 0, and that was sort of overkill. It would have been good enough if it were just 0 times something, which was 0. And so let's look instead at the quotient group Z4 times Z2. Remember, G for me was Z4 times Z4. And then you realize that my class that I care about, XY, is the restriction of a class on Z4 times Z2. So its obstruction has to be the restriction of the obstruction, and then you show that the restriction map on obstructions vanishes. So the whole obstruction vanishes. So that's that proves that this class has trivial obstruction. And this is kind of the only method I know in general to do this type of problem. You kind of keep taking a thing, you say, oh, there must be an obstruction, and you measure some part of it, and then you say, oh, well, since that part of it vanishes, then it comes from here, and then you write down some, like you say, but this part has to pull back from here, and then you prove it. Anyway, anybody who does like actual cohomology calculations knows that this tends to be the game of a constant kind of playing about like, well, oh, this has to pull back from here, but if it pulls back from here, then it has to pull back from there, and then its image over there will detect this, and that map is an injective, and that kind of thing. That's how you do that layer. So yeah, so now you believe me that there is a supercohomology class of trivial Majorana layer. And then the last thing I wanted to tell you was why this why having a trivial Majorana layer, why having a non-trivial Majorana layer prevents you from being a true gauge theory. And unfortunately, I think I have to say this too quickly because I have 5 slides in 10 minutes.
You can take your time. I think there are now a couple of calls. So Zhao Gang completed this comment. You're saying sort of in the EF, there are 2 classes, one with gamma equals to 0 and one with gamma non-zero.
Yes, this is
basically what you
correct.
were just showing, and then
This is exactly right.
Asking about when exactly you have higher form gauge groups in the AB class, where that the A equals to 0, when beta and gamma are 0, you can have higher form gauge groups. You might actually need A and B alongside beta.
Xiaogang's comment matches exactly the last slide I'm going to put up. Of course, it is something he already knew. And Nidu's question, I think I will answer in the last 5 slides. But let me tell you what sort of, so the new results are, first of all, that indeed this kind of bottom layer can be non-trivial and that you can have it. By the way, the example I gave was a group of order 16. It was Z4 squared. I'm pretty sure that there's no example smaller than that. I'm pretty sure this is the smallest group with a non-trivial, which has a supercohomology class of non-trivial Majorana layer. I couldn't quite finish the calculations for some of the groups of order 8, but I'm pretty darn sure that they don't work out. Like I'm pretty confident I know what the abstractions are in those cases. Okay, so now let me tell you why this bottom layer completely rules out having any higher form true gauge theory description. So suppose you have some higher form gauge group, I'll call it curly G. If there's any 2 form or higher part of curly G, then that's boring. You can kind of use some standard methods to get another gauge theory that doesn't have them. They just act by local operators. If they act non-trivially at all, then they kill the whole theory. And if they don't, then like basically what I'm saying is that a 2 form subgroup of curly G will be dual to a -1 form gauge theory, and those are easy to handle. So that's boring. So the only groups I have to care about are basically 2 groups. I have a 1 form part and a 0 form part. And now let me remind you what a digraph-Witten action on a 2 group looks like specifically in degree 4. So digraph-Witten action on a 2 group, well, you can compute, there's some Serre spectral sequence that computes this whole thing, but it's not useful. But I can restrict a cohomology class in the 2 group just to the 1 form subgroup. And on the 1 form subgroup, the restriction of my cohomology class is a class in degree 4 cohomology of a 1 form group, and degree 4 cohomology of a 1 form group, according to Eilenberg and MacLean, is the quadratic forms on that abelian group. So pick up a quadratic form. Any quadratic form has an interesting thing you can write from it. This is like nice, like very early 20th century math, maybe even 19th century mathematics now that I'm doing. So if you have a quadratic form on an abelian group, it has a thing called the radical. And the radical is the subgroup who's completely invisible to the quadratic form. And the flavor of the problem, the flavor of this gauge theory, will depend on what the radical is. One example is when the radical is so the radical by construction, it has the property that if Q of AB is equal to Q of B for all B, then in particular, Q of A is equal to Q of the identity element, which is just 1 for a quadratic form. So, the whole digraph-Witten action is trivial on the radical subgroup. And now this sort of idea of picking up a finite subgroup and gauging it away, the way that sort of Bardwaj and Tachikawa and then Tachikawa explained, this does apply in this case. So my whole group, my whole gauge theory has a dual description where I kill the radical subgroup. And the cost of killing the radical subgroup of the one form symmetries is I pick up a dual zero form symmetry radical group. But I end up with a new dual gauge theory whose shape, which has fewer one form symmetries and more zero form symmetries. So that's the first simplification. Why do I like to do that? Because again, I want to focus on the one form symmetries. They're the things that have the potential to give me interesting things beyond ordinary Dirac-Witten theory, in fact, beyond zero form Dirac-Witten theory. And so that's what I'm going to focus on. So now let me work out what is the restriction, like in this new gauge theory, what does the one form symmetry group look like? Well, oh, right. So what you find out is that because the radical of Q is completely invisible to Q, the quadratic form descends to the quotient. So, right, you have this just a projection map from A to A mod rad Q, and the rad and Q goes to U1. Now, this is not a homomorphism. It's just a function. It's a quadratic function, not a linear function, not a homomorphism. But the radical is designed so that at the level of functions, you still factor, and you get another quadratic form. And that is indeed the sort of quadratic form you see after doing this dual description. So what I'm telling you is that every higher form gauge theory is dual to a higher form gauge theory where there's no radical left in the quadratic form. So without loss of generality, there's no radical in the quadratic form. And now quadratic forms without radical come in two flavors. There's a sort of all bosons flavor and an emergent fermions flavor. The all bosons flavor is where the quadratic form is non-degenerate. So one of the basic things you can do with any quadratic form is you can write down a bilinear form. So that's like the kind of this bilinear form measures the failure of your quadratic form to be linear. It's like the second derivative of the quadratic form. And the bilinear form that you write down has some formula, and it might be a non-degenerate bilinear form, or it might be a slightly degenerate bilinear form. It might be that this bilinear form has just a Z2 kernel. And those are the only two possibilities if the radical is trivial. If the quadratic form is non-degenerate, then actually you can kill that part. But then you can pick up this whole A1 gauge theory. You can realize the whole, right? I wanted to do like a gauge theory for A1.G. Any gauge theory, anytime you have a gauge group which comes as an extension, you can write down that gauge theory by first gauging the normal subgroup and then gauging the base. And well, if the quadratic form is not degenerate, then gauging the normal subgroup just again returns you with an invertible theory, a trivial theory. And so this is just a plain G gauge theory. So that's boring. And the interesting case is when the A is this emergent fermion case. And that's the case whose Majorana layer I have to control. And now I'm going to just sort of tell you things and you're not going to understand them. So here's the way you do the bit is that you say, well, this problem is the same as a problem in fusion categories. Any abelian group with a quadratic form gives you an interesting braided fusion category. This was something at least known to Moore and Zyberg in their paper on sort of introducing half of these things, maybe earlier. In the case I care about, it's what's called a slightly degenerate braided fusion category. And the whole problem, like all the input information I've given you can be kind of rearranged into the data of a slightly degenerate braided fusion category with an action of my group. And now it's a problem in fusion category theory. And the problem becomes work out what the anomaly of this action is, or at least work out the Majorana layer of the anomaly of this action. And this is something that we've in the last few years gotten pretty good technology to do in the fusion category literature. And very briefly, it's sort of you start getting into higher algebra, you start saying, well, in general, there's like the automorphism group of your fusion category. There's something called the Brouwer, or maybe the Picard group, depending on who you are. Those words mean the same thing, so I just called it the Brouwer-Picard group. And really what I care about is I have a group mapping to op B, and the Majorana layer is the abstraction to this lifting problem. And then the last step of the proof is to realize that in this abelian case, there's a good theory of dimensions, which is valued in integers, and the theory of dimensions, which is kind of easy, and that lets you completely split this, so that in the case that this actually just splits completely if my braided diffusion category is abelian. And so in particular, any subgroup splits. So that that proves that Majorana layers are always trivial for these true gauge theories. And then actually I lied to you, but I'm not going to tell you the fix of the lie because I know exactly my time, but you can read it on the slide. I didn't lie to you in the case I care about. The theory everything I told you is exactly right when the extensions, when the thing I was calling kappa is trivial. When kappa is not trivial, the actual classification is slightly more complicated. And here's the final theorem. And indeed, as Shogun said, there are these two interesting classes. And the theorem says that in the class CF0, there is a dual gauge theory description. In fact, in that case, the Tachikawa style finite subgroup gauging just works and gives you a dual gauge, true gauge theory description. And in class CF1, not only does the Tachikawa method not work, but actually no method works. There is not any true gauge theory that describes those TQFTs. So thank you all for your attention.
Okay, thanks very much. Let's thank Theo. Are there questions? I think Xiaogang has unmuted himself.
Yeah, sorry, my microphone not working before. Yeah, I have a question about this this reduction of a higher gauge theory. Apparently, I don't know whether my understanding correct or not. You show that all the higher gauge theory in 3+1 dimension can be reduced to the particular higher gauge theory where the second layer only Z2. Can I understand that way?
That is a consequence of what I showed. So what I showed was that in dimension 4, any higher form, any two group gauge theory, if it is a true gauge theory, then it's either of class AB or of class CF0.
Okay.
And therefore has such a description, but that's not the method of proof.
Okay. You also mentioned this spin gauge theory, and so in some sense, you say this Z2F gauge theory, it just sum over a spin structure, which is almost like a summing over a Z2 gauge field.
Exactly.
I wonder whether the distinction from Z2 gauge theory is that here for the spin Z2 gauge theory, you need to assume space-time is a spin manifold. And you say if the space-time is not spin manifold, then maybe partition function equal to 0 or something kind of excluded.
That's right. So
otherwise it will be similar.
That's right. So any 4D TQFT at all, if you only evaluate it on spin manifold, so if you I mean, the way I would say it is actually about after tensoring with an invisible fermion. So, but equivalently sort of restricting to just spin manifolds, then you've thrown away some information when you did that. You threw away the information on manifolds that aren't spinnable. But after throwing away that information, then any 4D TQFT at all is what I would consider a gauge theory. Okay. Now, it's not a Digraph-Witten theory. It's a gauge theory for some sort of the appropriate type of gauge theory for spin manifolds.
Okay.
But it is a gauge theory. It is just a sum of G bundles. Well, in this case, of GF bundles.
Okay.
But what's interesting is that this Majorana layer obstructs it from being a true gauge theory on sort of as a bosonic, as an oriented theory.
Yeah. Okay. Yeah. Thank you.
So you say that this theory that you presented admits a topological boundary condition, which is Neumann for Z2F.
That's correct.
So that means I
And
can
that's
on the
true
boundary.
for all, and that's true for any spin cage theory. There's always a boundary condition, which is Neumann for Z2F and Dirichlet for the rest of the fields.
Right. So now that means that for the 3D boundary, I can gauge Z2F and obtain a one-form symmetry on the boundary.
Yeah. Yeah.
And then I have a one-form symmetry and a leftover zero-form symmetry. But you're now saying that these don't
Yes.
combine to give a two-group symmetry.
That is exact. You have it exactly right. So yes, you have a Z2 one-form symmetry, and you have the leftover G symmetry, except you
So-
don't quite. So what happens is when there's a Majorana layer, then so secretly when you tried to gauge that, you had the like Neumann, right? So basically secretly there were some subtle choices that had to matter, and yeah, it's exactly basically what you said, that the Majorana layer interferes with compiling all of the symmetries you have into Z21.G higher group.
But is it like an anomaly then that you maybe can't gauge
Yeah,
the Z2?
yes, I think it probably for some definition of the word anomaly is exactly an anomaly. I was just at a conference last week where one of the talks consisted of, well, discussion talks consisted of the crowd just like listing every word that none of us liked. And we all agreed that the word duality was crap. We all agreed that the word anomaly was terrible. But so,
Okay.
so up
Okay,
to
let me be
believing
more
what you think
specific.
anomaly means.
It's some anomaly that basically obstructs gauging the Z2F. So it's a Z2F kind of
Yeah,
anomaly.
where the anomaly shows up, you might call it like a mixed anomaly or a mixed term. Where what it shows up with is the Majorana layer obstructs the thing that Laksha knows very well how to do. That thing that Laksha knows very well how to do is something you can do for like the absolute theory. The Majorana layer obstructs you from doing it in a G equivariant way.
So I'm confused about the final symmetry group that we obtain. If we have a one-form symmetry and a zero-form symmetry and nothing else, but they do not combine to form a two-group symmetry. What else is there?
Right.
Is it?
So what I'm saying is that you right. See what's happening here is that when you look at the boundary, when you look at this like boundary condition which does exist, which is Neumann for the Z2F fields, and you try to implement the G field, so it looks like it's Dirichlet for the G field. So as you said, it looks like it should have a G symmetry on it, and it doesn't. It's like that what happens is it sort of has a G symmetry, but the algebra of the G fields doesn't close. And you would say, well, that's fine if what you were doing was when you composed a sort of little G defect with a little H defect, you'd have been completely happy if that was the GH defect, except for some one form piece. That would have just meant that you had a non-trivial extension. But instead, when you try to compose a little G defect with a little H defect, you pick up something which looks like Majorana spin chain. And so you don't have, what you don't have is an actual G symmetry on the boundary. You have you have a double cover of G that acts. Specifically, you just take the double cover of G, who is classified by the Majorana layer. Now you've trivialized the Majorana layer, and now it acts on the boundary, but it acts somehow redundantly on the boundary. So your choice is either you have something like which is like not a faithful action, so it was wrong, or you have something which isn't an action at all, so it was also wrong. That's what you see on the boundary.
Oh.
So this is worse than an 't Hooft anomaly. It does deserve the name anomaly. It's just a type of anomaly which is slightly worse than an 't Hooft anomaly.
So are you saying I cannot gauge Z2F using this bound? This
Well, you
boundary
cannot.
condition doesn't correspond to gauging.
Yeah, I mean, when I said this sort of crazy thing, I said like it's Neumann for the Z2F fields, but this is nonsense because Z2F doesn't arrive when I first presented the theory. It wasn't a gauge theory. So what did I mean when I said the Z2F fields? What I really meant was I meant the dynamical spin structure. And the theory with a dynamical spin structure has a boundary, which is just where the spin structure on the boundary is allowed to be dynamical. And that's the one I'm calling Neumann because the Neumann boundary condition for a gauge field is where the gauge field is also dynamical on the boundary. And so in some sense, it's like the boundary is already has Z2F gauged.
So that means I have a bosonic theory.
Yeah, everything's bosonic.
Yeah, and so yeah, and I have a 1 form symmetry and a 0 form symmetry, which does not form two groups. So
That's exactly
I
right.
don't know. What is
what's wrong is when you said you had a 0 form symmetry. You didn't quite have a 0 form symmetry. You had a thing which wanted to be a 0 form symmetry, but it had an ambiguity, and you thought you had it because you thought that ambiguity was invisible on the boundary. And I'm telling you that actually you can still see it.
Okay, thanks.
Yeah, I'd like to ask again the question about the reduction of the higher gauge theory. I try to understand your result. If that's basically you think about the bosonic higher gauge theory defined on maybe triangulated space-time lattice, and then in 3+1 dimension, it seems you show that this bosonic higher gauge theory can be reduced to a particular higher gauge theory where the second layer is only Z2. And that means this bosonic higher gauge theory can only realize the AB class and the EF0 class, cannot realize the EF1 class. So that's
what I'm claiming.
Okay, good.
That's my claim.
Yeah. So basically, then this bosonic higher gauge theory is a special case for the state-sum formulation for this topological theory. So then the EF1 actually can be realized by this some kind of state-sum formulation, but not by higher gauge formulation. That's also what you think.
Yes, that's another way of saying what I'm saying, exactly.
Okay, yeah, thank you. Yeah.
And somebody like Dan Freed would perfectly happily admit these ZF1 things because they are still given by a finite path integral. Yes, it's not that they're like a perfectly mild thing. It's still a finite path integral. Yeah. It's still just given by a Lagrangian, and there's nothing crazy about these. They're just not gauge theories. They're something else.
Yeah.
The last, I think the sort of PS, I think that's about that. This is maybe the smallest example you think.
Oh yeah.
But, is there sort of a sense in which you could give a criterion for which G's this could actually happen? So here you gave the Z4 squared example, but
I'm dubious to have any kind of universal criterion that goes better than just like, well, you reach inside and you do some hard cohomology calculation. In general, like, calculating cohomology of finite groups is a non-trivial problem in algebraic topology. It's just, we have lots of methods, but it's not like we can, it's like you do get to write a paper when you do it. I mean, so, I have a whole paper that just calculates like one cohomology group of one finite group, and it got into a really good journal. So this is like.
Okay.
So yeah, returning back to this the theory that you obtain on the boundary after gauging. Do you have some
Yeah.
idea what the symmetry structure of this is? Is it non-invertible?
Yes, so I mean, the symmetry
Sounds
structure is always, there's always a fusion 2 category so this is like the boundary's 3D. So you expect to implement zero form symmetries as surface operators in 3D. So you expect to implement them as objects in a fusion 2 category. There's always a fusion 2 category. And it's a fusion 2 category, which is not of the form Vec join G for G 2 group.
But do you know more details about this category? So we know that.
Oh, I mean, I can write
what-
it down exactly. Yeah, you just like, it is the fusion 2 category whose name is, so if you, let me give some, what's a good color to write? Purple, I guess, might show up against yellow, maybe not. Maybe I'll just write it in black. So if you take whatever your full supercohomology class is, you take your full supercohomology class, and then you take like S spec omega join G. And the point is that that formula parses. No, then now you can't see it because I erased it. Because I apparently don't know how to use my, let me just write it again. So you take your full supercohomology class, and you can even put in a twisting, and then the form that sort of the expression S spec omega G parses perfectly well for any supercohomology class at all. It's a perfectly good thing. This is a G-graded extension of S-spec. If you speak fusion category language, you really like G-graded extensions. You know that in general, G-graded extensions of anything are classified by some ENO extension class, which lives in some cohomology theory, some typically generalized cohomology theory. For SVEC in particular, the typically generalized cohomology theory that classifies extensions is the cohomology theory called supercohomology.
I mean, after
And
gauging
so this is a
Z2F,
perfectly good object. I only know one gapped boundary condition. I only know one topological boundary condition which exists universally. I don't know if it's the one before or after gauging something on the boundary because I can't keep track.
This
of
is
that,
the
but
one
it's-
where
this is-
Z2 is basically, the Z2F is Neumann.
This is the one where Z2F is Neumann
Right.
and the G is
And
Dirichlet.
I think the thing that we keep asking is if you can gauge, so change the boundary condition for Z2F.
No.
No,
it's
I mean,
Neumann.
Z2F has, like, there is a Z2-1 form true symmetry on this boundary, which is sourced by the fermion line inside of S-spec. And that, like, but this is the name for the full fusion 2 category on the boundary. And you could ask me which are the invertible subcategory of it, but that's the wrong question. As we've been kind of all learning, like, the invertible symmetries don't tell you the whole story. And different invertible symmetries can be somehow equivalent because they might be related by a non-invertible defect. And so you could ask me what is the invertible subcategory of this, and I'll tell you the answer. So let me give this a name. Let me call this C. It's some fusion 2 category. The invertible subcategory of this is something of the following shape. There's a C cross in degree 2, just the scalars. There's a Z2 in degree 1, just the invisible fermion. And there's a double cover of G. There's some sort of double cover 2G in degree 0. Not 2G in the sense of 2 group. In finite group theory literature, we tend to, like, anyway, maybe I'll write this out more carefully. There's a Z2 dot G living in degree 0. But the problem is that this Z2 is not really there, because the two things in this Z2, if you take two different elements in G and you take their two lifts to Z2 dot G, they're related by those are two different invertible defects on the boundary, but they're related by a non-invertible defect. And so they're not really different. You know about, if you know about one of them, you know about the other, and you didn't learn, like, they were already forced, this Z2 was sort of forced to be there already by this Z2. So this is not the right way to, I mean, this is not the true symmetries in the boundary. This is maybe what you'd call like, this is something else. Because you already know this isn't the true symmetries in the boundary because like I wrote down some scalars, and those scalars aren't really acting on the boundary, they're just scalars. So writing down the group of all invertible operators is never the right thing.
So you're saying the two elements in Z2.G which project to the same element in G they have a morphism between them, so they are not.
Yes,
they're
that's what I'm
in
saying.
the same Schur component.
That's right, they're in the same Schur component, and so you should not count them separately.
Okay.
But so this is the fusion category, the fusion 2 category on the boundary. And it only has G many Schur components. So to the leading order, there's a G zero form symmetry, but there isn't really a G zero form symmetry. Like,
I see. Okay. Thanks.
Sorry, are there different objects in the same Schur component related by gauging this fermion line? Is that?
yes, that's right. That's exactly right. So as soon as you knew about the fermion line, you knew how to move around a Schur component.
And gamma is the data of which junctions have a fermion line, right?
Gamma is this extension.
But
beta is this extension and alpha is this extension.
so gamma wasn't.
Gamma tells you when you take a G surface and an H surface and try to just stack them together. Gamma tells you, do you get the GH surface or do you get the GH surface gauged by a fermion line?
I see. Okay. And why does this pose an obstruction to gauging the fermion line? I can see that it might pose an obstruction to gauging G.
You can't gauge the fermion line. You can never gauge the fermion line. This Z2 one form symmetry has a non-trivial anomaly. Its anomaly is called -1 to the square 2. So you cannot gauge it in the usual sense. You can couple the spin structures and gauge it, but that after you've coupled the spin structures, my whole talk evaporates.
I see. So gauging might involve putting some other transparent fermion or something like that, but that's changes many
once
things.
You add some other, and if you go and like willy-nilly add transparent fermions, you start throwing away information. You know, think about just like toric code versus the all fermions version of toric code. Those are the same if you put in another transparent fermion, but they're really different as 3D TFTs.
Can I ask an unrelated question?
Okay.
So how do you, on a lattice, how would you construct a model which has a non-trivial gamma? What kind of, is there some intuition as to how to build it up from zero-dimensional blocks?
I mean, maybe Xiaogang can say more, but I told you a boundary condition. I told you that this theory has a favorite boundary condition, which is this one that's sort of like morally Z2F is Neumann and G is Dirichlet. And I told you the full category of the full fusion 2 category of operators in the boundary. And that's the same as telling you that the full theory is the kind of Teraya-Vera model or Walker-Wang model or whatever you want to call it, built from this fusion 2 category. So I'm not sure, I mean, I don't believe anyone has, actually in this particular case, this fusion 2 category is really nice. It's very spherical. And so the state sum model you can look up in Douglas Reuter. But in general, maybe, I don't know if anyone's written down like a general way of getting state sum models out of any fusion 2 category, but for this one, I think you could just use Douglas Reuter to get the 4D state sum model.
Right, but instead of a state sum, if we're interested in a Hamiltonian, is that
Yeah,
possible?
I think, you know, I think most people that I talk to, so as far as I know, there is not a paper that writes down Hamiltonian models from fusion 2 categories, even from spherical fusion 2 categories. It seems that most people believe that having a, say, commuting projector Hamiltonian model and having a state sum model, kind of the Walker-Wang versus Tarab-Vero, that somehow there's very little daylight between those, then there should be some general machinery to go between them. But then every once in a while, I run into an expert who thinks that they are fairly different. And it's not something I've tried to work out. But I think basically morally, the information of a state sum model and the information of a commuting projector Hamiltonian model are certainly in one direction. I think like if you know a state sum model, then you can definitely write down a Hamiltonian model because you just like put your state sum in space-time and then write down its Hilbert space, and then you like look at it, and just from the state sum model, you sort of recognize some commuting projector Hamiltonian. But as I said, I haven't tried to do this myself. Xiaogang wants to explain how to do it.
Yeah, indeed, there's a way to convert every state sum model into commuting projector model. And the state sum model have a property of this retriangulation invariance that translates into all these projector are commuting, you know, doesn't matter how you do it.
That's right.
And actually, there's a physical way to understand this gamma, in the sense that in the gauge theory, you have this one-dimensional gauge flux in space. And but when you have a fermions, this gauge flux may contain Majorana chain, you know, this Majorana spin chain. Because the Majorana spin chain is invertible, so there's ambiguity. You don't know which gauge flux have a Majorana chain, which gauge flux have no Majorana chain. And this gamma represent abstraction to assign this. So we say this gauge flux have no Majorana chain, that gauge flux have a Majorana chain. To assign to have this consistent assignment is not always possible. Now gamma representing such abstraction, because the gauge flux have their own fusion property. The two flux fuse to get your third flux. And so there's some abstraction of us to identify which gauge flux line have a Majorana chain, which gauge flux have no Majorana chain. There's some abstraction. And I think that is a way to, one way to understand this gamma. But however, this G order 16 is a trouble, because yeah, there is a cohomology equation you can just solve maybe by computer. But the G16 is very large, so the computer calculation is a very large calculation. So so computing this explicit form of the cocycle representing gamma is a pretty challenging. Yeah, it's just numerically challenging, but you know, the mathematically is, I think it's quite clear theory. Just to get a concrete example is challenging.
I see. So the local Hilbert space has Majoranas, right? In addition to other degrees of freedom.
No. These bosonic models, the local Hilbert space is just a boson, just qubits.
So how do you arrange for the some G?
The reason you have a Majorana, the reason you have emergent fermion. Emergent fermion can form a Majorana chain, which are invertible. And then when you have this gauge flux, which is also line-like in space, then you don't know whether this gauge flux also contain a Majorana chain or not contain Majorana chain. So it's because they're invertible, it's hard to tell. And so in the EF1 or EF0 is that we can consistently determine we can consistently define a set of gauge flux line which have no Majorana chain, then just like ordinary gauge theory with emergent fermion. But the EF1 is that we cannot consistently determine a set of gauge flux line which have no Majorana chain, because that would be there's some abstraction. yeah, it's a little, yeah, that's only, that's a level of my understanding. I couldn't explain more in more detail. Yeah, there's some abstraction here.
Thanks.
Okay, so I think let's thank Theo again for his nice talk and also for the long discussion. And we can switch off maybe the recording.
Yeah.
And